Welcome to Astronomy Daily, your source for the latest space and astronomy news. I'm Anna.
And I'm Avery. Today is Thursday, February 5th, 2026, and we've got a great lineup of stories for you today.
We certainly do. We'll be covering a major victory for dark sky preservation, groundbreaking measurements of Jupiter's true size, a monster sunspot currently facing Earth, mysterious Martian weather, some frank talk from NASA about the SLS rocket, and how red giant stars destroy their own planetary systems.
Quite the cosmic menu. But before we dive in, a quick reminder that you can get more space news and community discussion at astronomydaily.io, and you can find us on social media at AstroDailyPod across all platforms.
All right, let's start with some good news for astronomy. Avery, what's happening with Earth's darkest skies?
This is a story that really highlights how fragile our connection to the night sky has become, Anna. Astronomers around the world are breathing a collective sigh of relief after plans for a major industrial plant near one of Earth's darkest sky locations have been canceled.
Oh, that's wonderful news. Where was this proposed plant going to be built?
The development was planned near the Roque de los Muchachos Observatory in the Canary Islands, which hosts some of the most important telescopes in the Northern Hemisphere. This site is renowned for having some of the darkest, clearest skies accessible to modern astronomy, and the proposed industrial facility would have introduced significant light pollution to the area.
I can imagine the astronomical community was pretty concerned. These pristine observation sites are becoming increasingly rare.
Absolutely. What makes this particularly significant is that it represents a growing recognition of the scientific value of dark skies. The cancellation came after sustained advocacy from the astronomy community, who emphasized not just the local impact, but the global scientific importance of preserving these observation sites. With light pollution spreading worldwide, losing access to naturally dark skies would be devastating for ground-based astronomy.
It's encouraging to see that science preservation can still win out over industrial development. These observatories represent decades of investment and irreplaceable viewing conditions.
Exactly, and it sets an important precedent for protecting other astronomical sites around the world. The International Dark Sky Association has noted that this decision could strengthen arguments for dark sky preservation elsewhere.
Great to hear some positive environmental news for a change. Now, speaking of observations from those pristine sites, let's talk about what we've learned about Jupiter. NASA's Juno mission has completely redefined our understanding of the gas giant's size and shape, hasn't it?
It really has, Anna. This is one of those discoveries that makes you realize how much we still don't know about even our most familiar planetary neighbors. Juno's precise measurements have revealed that Jupiter is both larger and more oblate than we previously thought.
When you say oblate, you mean it's flattened at the poles, right?
Exactly. All rotating bodies experience this to some degree. Even Earth bulges slightly at the equator. But Jupiter's rapid rotation makes this effect much more pronounced. What's new is just how pronounced it actually is. Juno's gravity measurements have shown that Jupiter's equatorial diameter is slightly larger than our previous estimates, while the distance between the poles is actually smaller. The planet is basically wider and flatter than we realized.
So what caused this miscalculation? I mean, we've been observing Jupiter for centuries.
Well, measuring the size of a gas giant with no solid surface is trickier than it sounds. Earlier measurements relied primarily on optical observations, essentially looking at where Jupiter's atmosphere becomes opaque. But Juno uses extremely precise gravity measurements as it orbits the planet. By measuring tiny variations in how Jupiter's gravity affects the spacecraft's trajectory, scientists can determine the planet's mass distribution with unprecedented accuracy.
And I assume Jupiter's rotation plays a big role in this shape.
Absolutely. Jupiter rotates once every 10 hours. That's incredibly fast for something so massive. This rapid spin creates enormous centrifugal forces that push material outward at the equator. What Juno has revealed is that this effect penetrates much deeper into the planet than we thought. The measurements suggest that Jupiter's interior structure, including how its metallic hydrogen layer behaves, is more complex than our models predicted.
This probably has implications for understanding other gas giants too, both in our solar system and around other stars.
Definitely. Understanding Jupiter's interior helps us refine our models of how gas giants form and evolve. And since we can't exactly drill into Jupiter to see what's inside, these gravity measurements are the next best thing. Every new piece of data from Juno helps us understand not just Jupiter, but the entire class of giant planets.
Fascinating stuff. It's amazing that after all this time studying Jupiter, we're still discovering fundamental things about its basic structure. Now, let's shift from distant Jupiter to our very own sun, which is putting on quite a show right now. Avery, there's a massive sunspot facing Earth at the moment.
There certainly is, Anna, and it's a monster. The sunspot currently facing Earth spans about 15 Earth diameters across. That's roughly 120,000 miles. To put that in perspective, you could fit 15 Earths side by side across a single sunspot.
That's genuinely hard to wrap your head around. And I understand people can actually see this with the right equipment.
Yes, but this comes with a crucial safety warning. Never look directly at the sun without proper solar filters. This can cause permanent eye damage or blindness. However, with proper eclipse glasses or solar filters designed specifically for solar observation, amateur astronomers can spot this sunspot fairly easily. It's large enough to be visible even with modest magnification.
What exactly is a sunspot for our listeners who might not know?
Sunspots are regions on the sun's surface where powerful magnetic fields break through, temporarily suppressing the hot convective currents that normally transport heat from the sun's interior. This makes these regions cooler than their surroundings, around 6,500 degrees Fahrenheit, compared to the normal surface temperature of about 10,000 degrees. That temperature difference is why they appear dark against the brighter background.
And these magnetic fields, there would cause solar flares and coronal mass ejections, right?
Exactly. Large, complex sunspot groups like this one have tangled magnetic field lines that can suddenly reconnect and release enormous amounts of energy. This particular sunspot is being closely monitored because of its size and complexity. When these magnetic structures become unstable, they can unleash powerful solar flares and potentially hurl billions of tons of charged particles toward Earth in what's called a coronal mass ejection, or CME.
Should we be concerned about potential impacts on Earth?
Space weather forecasters are definitely keeping a close eye on it. A large CME directed at Earth could affect satellites, power grids, and radio communications, and could produce aurora displays at lower latitudes than usual. However, our sun monitoring satellites like SOHO and SDO give us advance warning, typically several days before CME arrives. So while this sunspot certainly has the potential to be active, we have the monitoring infrastructure in place to track any eruptions and issue warnings if necessary.
It's one of those reminders that we live inside the sun's atmosphere, in a sense. We're constantly bathed in the solar wind.
That's a great way to think about it. Earth's magnetic field shields us from most of the effects, but we're definitely connected to our star's activity. And for amateur astronomers, it's a rare chance to see solar activity on this scale with safe solar viewing equipment.
All right, from solar weather to Martian weather. Avery, there's been an unusual storm on Mars that's revealing something new about the red planet.
Yes, and this is a particularly intriguing discovery because it challenges some of our assumptions about Martian meteorology. Researchers have observed an unusual storm system on Mars that's providing new insights into the planet's atmospheric dynamics and what lies beneath its dusty surface.
What made this storm unusual? I mean, Mars is famous for its dust storms.
True, but this storm exhibited behavior that didn't fit our standard models of Martian weather patterns. The storm's movement and structure suggested it was being influenced by subsurface features. Essentially, the topology and composition beneath Mars's surface was affecting how the storm developed and moved across the planet.
So the ground itself is influencing the weather. How does that work?
It's similar to how mountains on Earth affect weather patterns, but Mars has some unique factors. The thin Martian atmosphere, less than 1% of Earth's atmospheric pressure, means that surface features have a proportionately larger impact on atmospheric circulation. Additionally, variations in surface temperature due to different rock and soil composition can create localized heating patterns that drive atmospheric motion.
And what did the storm reveal about what's underground?
The storm's behavior suggested there are variations in subsurface composition that weren't previously mapped. By tracking how the storm responded to these hidden features, scientists could essentially use the storm as a probe to detect what's below the surface. It's a bit like how doctors use ultrasound. You're using one thing to indirectly sense another.
That's a clever way to gather geological information. Are there implications for future Mars missions?
Definitely. Understanding these subsurface features is important for several reasons. First, they could indicate locations where subsurface water ice might be present. Second, they help us understand Mars's geological history and how the planet evolved. And third, for future crewed missions, knowing what's underground is essential for landing site selection and resource utilization. You want to land somewhere with access to useful materials.
It's fascinating how atmospheric science and geology intersect like this. One storm can tell you so much about an entire planet.
Exactly. And it's another example of how every Mars observation opens new questions. The more we learn, the more complex and interesting Mars becomes.
Indeed. Now, speaking of complex and interesting, let's talk about NASA's Space Launch System. There's been some remarkably frank discussion from NASA about this rocket's future, hasn't there?
Yes, and it's notable precisely because NASA officials are rarely this candid about program challenges, Anna. For the first time, NASA is publicly acknowledging what many industry analysts have been saying for years. The Space Launch System has fundamental cost and sustainability issues that need to be addressed.
This is the rocket that's supposed to take astronauts back to the moon, part of the Artemis program, right?
That's correct. The SLS is the most powerful rocket NASA has ever built, designed specifically for deep space missions. It successfully launched Artemis 1 in late 2022, sending an uncrewed Orion spacecraft around the moon. And it's scheduled to launch Artemis 2, the first crewed lunar mission in over 50 years. Though that timeline keeps shifting.
So what's the issue? The rocket works, doesn't it?
The rocket does work. When it flies, it performs beautifully. The problem is the economics. Each SLS launch costs roughly $4 billion, and the system can only fly about once a year with current infrastructure. For comparison, SpaceX's Starship, which is also designed for deep space missions and has greater payload capacity, is projected to cost a tiny fraction of that per launch and could potentially fly dozens of times per year.
$4 billion per launch. That's hard to justify, especially when alternatives exist.
Exactly. And that's what makes these recent NASA fatements so significant. Administrators are openly discussing the elephant in the room, that maintaining SLS in its current form may not be sustainable for a long-term lunar or Mars exploration program. They're acknowledging that the program needs to either dramatically reduce costs or potentially transition to commercial alternatives.
This must be a difficult position for NASA. The SLS represents decades of development and enormous investment.
It absolutely is. There are also political considerations. The SLS program supports jobs across multiple states and has strong congressional backing. But NASA is facing budgetary pressure and needs to make realistic plans for sustainable exploration. The acknowledgement that SLS's costs are problematic is a significant shift towards having honest conversations about the future of deep space exploration.
What are the alternatives? Would NASA switch to something like Starship entirely?
That's one option being discussed, though it's complicated. NASA has already contracted with SpaceX to provide a lunar lander version of Starship for Artemis missions, so there's already commercial partnership in place. Some proposals suggest using commercial heavy-lift rockets for cargo and potentially even crew, while others advocate for a hybrid approach. The challenge is that any major change would require congressional approval and significant replanning of Artemis architecture.
It sounds like we're at an inflection point for NASA's deep space ambitions.
We really are. This is one of those moments where honesty about challenges is the first step towards finding solutions. The fact that NASA is willing to have this conversation publicly suggests they're serious about finding a sustainable path forward, even if it means difficult decisions about programs that have tremendous legacy and political support.
Well, we'll certainly be watching how this develops. Now, for our final story, let's venture into the realm of stellar evolution. Avery, red giant stars are apparently destroying their own planetary systems.
They are, Anna, and this research gives us a rather apocalyptic preview of what will happen to our own solar system in about 5 billion years. Astronomers have observed how red giant stars, stars in their late evolutionary stages, systematically destroy gas giant planets that orbit too close to them.
This is what our sun will eventually become, right? A red giant?
Exactly. When stars like our sun exhaust the hydrogen fuel in their cores,
They begin fusing helium and expand dramatically. Our Sun will eventually swell to perhaps 100 times its current diameter, likely engulfing Mercury, Venus, and possibly Earth. But this research focuses on what happens to planets that survive the initial expansion, particularly gas giants at distances similar to Jupiter and Saturn's current orbits.
Though these planets survive the star's expansion, but not what comes after.
Precisely. As the star becomes a red giant, several destructive processes occur. First, the star becomes much more luminous. Our Sun will eventually be about 2,000 times brighter than it is now. This intense radiation heats the atmospheres of gas giant planets, causing them to expand and potentially evaporate. Second, red giant stars have powerful stellar winds that can strip away planetary atmospheres. And third, the star's expansion causes tidal forces that can alter planetary orbits.
That sounds like a recipe for planetary destruction. What exactly did the researchers observe?
They studied multiple red giant star systems and found evidence of gas giant planets in the process of being destroyed. In some cases, they detected the spectral signatures of planetary material being stripped away and falling into their host star. In others, they found gas giants with highly eroded atmospheres, clearly showing the effects of their star's evolution. It's like watching different stages of the same destructive process.
This presumably has implications for our understanding of how planetary systems evolve over time?
Absolutely. One of the key findings is that the habitable zone, the region where liquid water could exist, moves outward as a star becomes a red giant. Moons of Jupiter or Saturn, currently frozen ice worlds, might temporarily become habitable as our Sun swells. But this research shows that even if these worlds briefly enter the habitable zone, the gas giants they orbit are being actively destroyed by the dying star. It's a very dynamic and ultimately doomed situation.
It really puts our solar system's long-term future in perspective.
It does. Though I should emphasize, we have about 5 billion years before any of this happens, so there's no immediate cause for concern. But it does remind us that solar systems, like everything else in the universe, have life cycles. Understanding these cycles helps us interpret what we see around other stars and appreciate that the stable, long-lived solar system we enjoy is a temporary phase in cosmic terms.
A sobering but fascinating look at stellar evolution. It's one thing to know intellectually that the Sun will eventually die, but quite another to see the detailed process of what happens to the planets.
Exactly. And who knows, in 5 billion years, humanity's descendants, if they exist, will likely have long since relocated to other star systems. Understanding how stars age and die is actually crucial for picking good long-term neighborhoods out in the galaxy.
That's a nice optimistic note to end on. Well, that's all we have for you today on Astronomy Daily.
And remember to check out our website at astronomydaily.io for more space news and to join our community discussions. You can also find us on social media at AstroDailyPod.
Thanks for listening and keep looking up.